we initiated discussion on characterizing convection enhanced heat transfer. Okay. So when you say conductive heat transfer, it really means that convection enhances heat transfer, and we will see in a short while how that's the case and why that's the case. Okay. So we considered an arbitrary shaped object, and there is a fluid which is flowing past this arbitrary shaped object, let us say at velocity v, and if the temperature is T infinity, and let us say that we assume that the temperature of the surface is maintained at Ts. So note that these two are measurable quantities. Remember that all through this course so far we have been talking about, like you must always have something called measurable quantities, you must compare with measurable quantities. So the temperature of the surface and the temperature of the fluid which is flowing past the object, these two are measurable quantities. So you would like to express and you would like to detect the heat transport coefficient, etc., everything in terms of these two measurable quantities. Okay. So that's why, supposing you take the local flux of heat transport Q double prime at any location, let us say, okay. So that's given by H, if it's the local heat transport coefficient, and if x vector is the position vector, okay. So that's now 3-dimensional coordinates, the position vector. So naturally x is going to be a function of the position, it depends on where you evaluate the heat transfer, where you want to find the flux, okay, and that multiplied by Ts minus T infinity, if I assume that Ts is greater than T infinity, okay. And we said that we can find total flux by simply taking an integral over the whole surface, dAs, okay. So now if we introduce a definition, okay, so note that it's a definition, if we introduce a definition of average heat transport coefficient, if I introduce the definition of average heat transport as 1 by As, so that's a cross sectional or the area average of the local heat transport coefficient, that's a definition. So if we introduce this definition, then we can write the overall net heat transfer rate is simply given by H bar into As into Ts minus T infinity. Okay. So when we really talk about Newton's law of cooling in the earlier framework, when we discussed conduction, we really meant it is the average heat transport coefficient. We assume that it doesn't change, and so it's the average that we were looking at. So in principle, the heat transport coefficient can be a function of position, it's a function of geometry, it's a function of the flow properties, etc. Okay. Alright, so let's turn back to mass transport. A similar scenario in mass transport would be, okay, so if the concentration of some species is CAS and if the bulk species concentration is CA infinity, okay, the framework is slightly different in mass transport, although the process is exactly the same. So supposing you have species A and species B, okay, both of them, it's a mixture which is flowing together, and let's say that only species A is diffusing out, species A is transported from this surface to the fluid, okay. So the diffusion process would be, we can assume that B is in excess, we can assume that species B is in excess, and we could assume that equimolar counter diffusion, and therefore what we are really looking at is transport of species A to the bulk fluid outside, and so what will be the mass transport flux? what will be the flux at any location? If I assume that CAS is greater than CA infinity, what will be the mass transfer flux? So note that heat and mass transport are similar, right? So you have some mass transport coefficient, which is again a function of position, multiplied by CAS minus CA infinity. Okay, so if I call this N double prime, N is the symbol I use for mass transport rate, and N double prime is the flux. Okay. So therefore, the net mass transport rate is given by integral over the whole surface So what is CAS? Is it a measurable quantity? Remember that when we discussed heat transport, we said that Ts and T infinity are measurable quantities. Is CAS a measurable quantity? Supposing you have an interface, right? So this is an interface between two different phases. This is a, let's say, a solid phase or a fluid phase, and this is a gas phase. Okay? Yeah? What is measurable? Where? So mole fraction of A in both of the phases. Supposing I call this as CA bulk, okay? So that's the bulk concentration in that phase, and CA infinity is the bulk concentration in the gas phase. What is CAS? Will that be same? So what will it be? How do we find CAS? Is it a measurable quantity? It's the concentration at the wall. So how do we find? Let us assume that it's a well mixed system inside here. The bulk concentration is the same everywhere. Is CAS still measurable quantity? Remember some of the concepts you have learnt in thermodynamics and probably transport also. So what is the balance that you would write at every location for this problem? Excuse me? Well, not really. What matches here is not the exact mass transport rate with respect to bulk concentration and the mass transport rate outside. That's not the conserved property. What's the conserved property here? Have you heard chemical potential? Must have heard chemical potential, right? So what you have to match at the boundary is actually an equilibrium between the species which is present in the gas phase and the species which is present in the bulk phase. Okay. So the correct way to do is, so at the interface, there will be an equilibrium between the two phases. So that, which means that the chemical potential in the gas phase should be equal to the chemical potential in the liquid phase or a solid phase, right? So the chemical potentials are equal. So at the interface, the chemical potentials are equal, and therefore, if you actually balance the chemical potential, you will find that CAS is actually not the bulk concentration, it's actually the equilibrium concentration. So CAS is the equilibrium concentration of species A. Okay. Now what it means is that unlike in the case of heat transport, okay, where you supply heat, the material is going to have a certain capacity, so it's going to take energy and the temperature is going to increase. That's not the case with mass transport. So you always have the issue of what is called saturation. There is only a certain amount of solubility of a particular species in a given medium, right? You cannot add more species to it if you are above the solubility limit. So unlike in mass heat transport, a system does not have an infinite capacity to take up mass. There is an upper limit, and that upper limit, the correct way to balance the upper limit is actually by equating the chemical potential. And so what equilibrium concentration really means is that what would be that concentration based on the solubility of the species in these two phases, what will be the equilibrium concentration if the chemical potential has to match. Okay, that's what that interface concentration is. So it is in principle a measurable quantity. If you know the bulk concentrations of two phases, and if one can actually find out what is the chemical potential, we know the relationship from thermodynamics, and we should be able to find out what is the interface concentration. So it is in principle a measurable quantity, but not a direct measurable property. So the direct measurable property are the bulk concentration of the species in the solid or the fluid phase, and the bulk concentration in the fluid gas phase, that is Ca infinity. Right, if you assume in heat transport case, the question is, will there not be a temperature gradient? So note that I said it's a well mixed system. So CAB is the bulk concentration everywhere. Similarly, if you assume that it's a well mixed system where the temperature is uniform, it's the same scenario. The only difference is that there the system actually can take more energy and it will lead to increase in the temperature. That's not the case with the liquids. That's not the case with mass transport. There is an upper limit on how much you can pump, and that is based on the solubility of that species in that medium. Unlike in heat transport, where you supply energy, the energy is going to be stored and you increase the temperature. That's not the case here. So it's not that you can infinitely increase the temperature. I mean, it doesn't happen really in heat transport, but in principle you can infinitely increase the temperature. There will be change of phase, etc. We will not deal with that. But in principle it can take energy more and more, but that's not the case with respect to the mass transport. So if you assume that phases don't change, then in heat transport you can continue to supply heat till there is a phase change. After that the process is slightly different. So, but that's not the case with mass transport. So there is no such limit as to phase change, but there is an upper limit called solubility limit. So CAS is essentially obtained by equating the chemical potentials, and that's the equilibrium concentration at the interface. So right now what we will do for rest of the convection topic is that we will assume that we know how to measure the interface concentration CAS, and we will assume that the concentration gradient is CAS minus Ca infinity, and in fact that's the correct concentration gradient. Okay. Excuse me? We are not talking about heat transport, we are talking about mass transport. We need concentration gradient. If there is no concentration gradient, there is no mass transport. The only question is what is the correct gradient. When it comes to heat transport, we said that the temperature gradient is the difference between the bulk temperature in that phase if it is well mixed and the bulk temperature in the fluid outside. That's not the case when it comes to mass transport. The interface concentration, the equilibrium concentration can actually be different from the bulk concentration here, because the equilibrium concentration will specify based on the solubility what is the maximum that it can take. Okay. So it's very important to understand this distinction that here we are not looking at bulk concentration, whereas in heat transport one can actually specify bulk temperature as one of the temperatures in the temperature gradient.
Because suppose the solid is at a higher temperature than the gas, and even if I assume it is it can't be like just the temperature of gas at the surface also. It will decrease, and for the gas, when the gas is below the surface, the temperature will decrease because of things like boundary layer, etc.
We are going to talk about, but note that the boundary layer is in the fluid phase, not in the solid. That we are going to see. So here we are talking only about what's happening inside this medium. When you talk about boundary layer is actually outside that media, which is actually in the fluid phase. We are going to talk about that because boundary layer concept is for the fluid phase, not for the solid phase. Now we are only trying to define what should be the reference temperature inside this phase and what should be the reference concentration in this phase. If we assume that the system is well mixed, we assume that there are no gradients inside, then the bulk temperature is the reference temperature for this particular phase, and the equilibrium concentration is the reference concentration, not the bulk concentration. It depends on the size of the system. Supposing if you use remember the lumped capacitance method we talked about, if you can maintain your dimensions such that you can maintain a uniform temperature and uniform concentration, why not? It's possible, it's very much possible. Okay, so similarly we can define what is called the average mass transport coefficient. You can define average mass transport coefficient. Okay, so Hm bar, which is the average mass transport coefficient averaged over the whole surface area. So that will be 1 by As integral over the surface into dAs. So using the average mass transport coefficient, we can now define the net mass transport as Hm bar into As A into D. Okay. So that's the net mass transport rate based on the average mass transport coefficient. Okay. Alright. So supposing if we take a flat plate, suppose we take a flat plate. Okay, so we have a flat plate and let's say it's maintained at some temperature Ts, okay, and we have fluid flowing past this flat plate at let's say velocity v and T infinity. So the average heat transport coefficient H bar will be 1 by L integral between 0 to L. So if the length of the plate is L and if this distance is x, this direction is x, maybe H times dx. Okay. So I assume that it's a uniform cross section, uniform length in the other direction, and so the other plane is infinitely long, and so the heat transport coefficient is essentially averaged over the length. And similarly one can write a mass transport coefficient which will be 1 by L 0 to L Hm times dx. So that's the average heat transport and average mass transport for flow past a flat plate. Okay. So now comes the question of what happens inside the fluid phase. Okay. So that's the whole aspect that we are going to discuss, how to find out the heat transport coefficient in this phase. Okay. So that's what we are going to find out. So whenever there is a fluid which is flowing past an object, okay, so you must have studied in your fluid mechanics course that there is going to be a boundary layer, right. So as soon as the fluid reaches the, it starts seeing the flat plate, what will be the velocity of the fluid at the boundary, at the interface? The velocity is 0, right. So suddenly, so supposing if I call this as y direction, okay, and this is x direction, okay, and suppose I specify that u or v infinity is the velocity of the free stream fluid, that is before the fluid actually sees the flat plate, what is the velocity of the fluid, and if I assume that it's a flat profile, that's not a bad assumption to make. Then if I say u is the x component velocity and v is the y component velocity, okay, what is u and v at y equal to 0? U equal to u at y equal to 0, that's 0, right, because it's an interface where the flat plate is not moving, it's a solid plate, and so the fluid is now in contact with the flat plate at that location, and so suddenly the fluid comes to rest because there is friction, and so the fluid is not allowed to slide past the flat plate, and therefore the fluid particles will come to rest. Okay. So the velocity, x component velocity at y equal to 0 is 0. So the fluid is not made to move in the other direction. What about the y component velocity? V at y equal to 0. That's also 0. So fluid is rest, fluid is at rest. So when fluid is resting, it means that all the components are 0. So u and v, the x component and the y component velocity at y equal to 0 is always 0 because of no slip boundary condition, right, because there is no slip, the fluid doesn't slip along the flat plate, and therefore the velocity is 0. So that has an important implication in heat and mass transport. So what's the mechanism of heat transport at the boundary? What's the mode of heat transport? We said there are 3 modes, right? Conduction, convection and radiation, right? So because the velocity is 0 at the interface, the actual mode of heat transport from one phase to another is actually conduction. So this has a very, very important implication that the mode of heat transport, heat or mass transport, at the interface, very important, at the interface is conduction or diffusion. Okay. So therefore, the mode of heat transport or a mass transport is essentially conduction or diffusion. So this observation actually simplifies a lot of things for us. Okay. So how does it simplify?